All right, so now we're almost everybody here. So now we're going to get into slide 46 and 47. And so far we talked about the standard way of presenting logistic and probit regression. Now we're going to talk about an alternative way of looking at those kinds of regressions. And it's an equivalent way. I want to say that from the outset. It's equivalent. No difference from a statistical point of view. So don't get confused in thinking that we are now introducing any more assumptions. So what we're going to contrast is the latent response variable formulation versus the probability curve formulation. What we looked at so far is the probability curve formulation. So in equation 67, we have that formulation, where f is that function that is a standard normal or logistic distribution function corresponding to probit or loaded regression. Now, the alternative formulation, the latent response variable formulation, it instead defines a threshold, and that's the tau that Linda was talking about, on a continuous u star variable, which is down here at the bottom of slide 46. You have the u star variable, and you have its distribution, perhaps it's close to normal, and it has a threshold tau. And tau functions in the following way, that when u star is below the threshold, you observe u equals 0. And when u star is above the threshold, you observe u equals 1. So for instance, think about a achievement test item in education. And u star is your specific knowledge that you have relevant to solving that item. If your specific knowledge exceeds a certain threshold, you get the item right, u equals 1. If it falls below that threshold, you get the item wrong, u equals 0. The notion here is that you might be close to the threshold and get it wrong. So the person who is close to the threshold, it can be quite different than the person who is far to the left here on u star and gets it wrong. Those two people both get it wrong. But one person is close to the threshold, and with just a little bit more studying, that person will get the item right. So the notion is that u, the observed dichotomous variable, is a crude classification, or crude categorization, I should say, of what you really want to measure, namely u star. But your measurement instrument is a little bit crude, and you only measure two categories. So that would say, for instance, it would be useful to have u low, medium, high, where medium then is sort of giving a person partial credit for an answer. You have some of the ideas right, but you don't get it totally right. So that would have you would have then three categories, and they would be ordered. And you would then have two thresholds. And as you bring in more and more categories, that case gets closer and closer to observing the u star variable. So that's one way of thinking about it in terms of a continuous u star variable. And the advantage of that is not only in terms of the crude classification idea, but also that u star then gets a linear relationship to x. And here we've written that in equation 68, gamma being the regression coefficient and delta being the residual. And you can then assume that the residual either has a normal distribution or, as we will see later on, a logistic distribution. And what we're going to find is that having a normal distribution for this residual of the u star, the latent response variable, gives you the probit regression. Same thing as probit regression. And if the residual delta is assumed to have a logistic density, it gives you logit regression. Just another way of thinking about it. I'm emphasizing that because sometimes, like on SEMNet, discussions come up, well, I don't believe in these underlying U stars. A person is either dead or alive. Well, that's irrelevant. It's just a way of thinking about it. It's not a different model. And in any case, I think even for dead and alive, the U star concept can be useful. In the sense that you have a disease process which moves toward a point, a breaking point, the threshold point, where you actually then are no longer. So this is serious matters, as you can tell. Anyway, so that's just telling the story in words. And on slide 47, you see it in utter statistical detail. Probability U equals 1 is the same as probability U star is greater than the threshold. And you go through the normal distribution function and get this expression here. There's one thing to remember, though, is that this residual delta in slide 46 on equation 68, yes, it is a residual that is well behaved, uncorrelated with x, mean 0, and yes, it has a variance, but the variance cannot be, that variance parameter cannot be separately identified from the other parameters. Otherwise, you would have one more parameter in logit and probit regression. So what you usually do is, in probit, standardize it to variance equal 1. This defines a probit model. So there is no residual variance parameter in probit, nor is it in logit. In the logit case, the standardization is not 1, but it is that variance for the logistic density that Linda mentioned, the pi squared divided by 3, the 3.14 squared divided by 3, the square root of which is 1.7, 1.8. So implicitly in the also in the logistic regression is an underlying U star and a residual that has a logistic density and a pi squared divided by 3 variance. It's not a parameter that you estimate, but it's a fixed value. And the difference in the probit and logit slopes differing by a factor of 1.8 is due to this different standardization, residual variance 1 versus residual variance pi squared divided by 3. So that then leads us to slide 48. Because sometimes you get the question, can you get standardized results with logistic and probit regression, and can you get R squared with logistic and probit regression? And I think that's related to this U star latent response variable formulation. If you have this on slide 48, the regression of U star onto X with a residual delta, that's a linear regression. You see that we don't have an intercept there because the intercept ends up in the threshold. You cannot identify both thresholds and intercept. You have to choose one or the other. But it's a standard linear regression apart from that. So you can talk about R squared as the explained portion of variance in the numerator and the total variance in the denominator. It's just that the total variance in the denominator then is a little peculiar in the sense that the residual variance is a constant C, 1 for probit, pi squared over 3 for logit. This R squared measure, though, has been suggested for logistic and probit regression by McKelvey and Zavoyna in 1975 in Mathematical Sociology, and it's been picked up in more current books. Snyder's and Bosker's multi-level book, for instance, also talk about that. And that is the R squared that we give in Mplus. How useful it is up to you to decide. Let me introduce that by way of talking about the bottom part of slide 48. We talk about standardized coefficients, first of all. Standardized slope gamma refers to the effect of X on U star. You know, it's standardized in the U star metric. So again, it's the raw coefficient gamma, estimated gamma hat, multiplied by the standard deviation of X and divided by the model estimated standard deviation of U star. So we give those standardized results. We also give them only standardized with respect to U and only standardized with respect to X. Now, the U star standard deviation then is this expression, the total variance that you have in the denominator for R square, taken with the square root. But how useful is that standardized coefficient? You know, a coefficient in linear regression tells you for a unit change in x, how much does the dependent variable change? Standardized coefficient in linear regression says that for a standard deviation change in x, how many standard deviation units or fractions thereof does the dependent variable change? Well, that's good and well for linear regression, but for logistic regression, although that statement is true for U star, it's not true for U. How do we say that? What do I mean? If you look at the picture on slide 48, and we're sorry we can't move this away to the side, well, I'll have it on both sides then so you can look at it. You have an x variable and the probability u equals 1 on the y-axis, and the probability curve is this S-shaped curve. Now you talk about a change in x. If x is, and we're going to make a distinction between two cases, x being low versus x being high. If you make a little change in x here, you're going to get a fairly small change in the probability on the y-axis. But if you make the same amount of change in x a little bit higher up on the x scale, where then the curve is steeper, you're going to get a bigger change in y. So for the same change in x, same amount of change in x, you get different changes in u depending where you are on the x scale. You know, if you're out in the tail, either low here or up high here, a change in x doesn't have much effect at all. But if you're in the middle where the curve goes steeply up, you have a lot of effect. That's a function of the nonlinear curve. You don't have that situation in the linear case. That is then an argument against standardized coefficients. Although they are useful for U star as a dependent variable, they may not be so useful for U. Okay, so that's an argument against using it. So we'll let you decide. And R square, is that really a relevant quantity when the residual variance cannot be estimated? It's sort of the numerator and the denominator are a little bit, they should be two separate parameter functions, and they are not. They're a function of the same parameters plus a constant. So it's a little bit of a funny R square as well. And you would see in the logistic regression literature, they don't work with R square typically. They don't work with standardized coefficients. And there are actually in the literature strong arguments against at least a standardization. So if you don't need to standardize, don't do it. All right, now let's go on to the ordered Polytomous case. We're going to talk about two Polytomous cases, ordered and unordered. And we're going to have two slides in front of us. And the slides tell the story in two different ways. On slide 49, we have the standard probability function formulation that we started with for the binary category outcome case. And on the right, you have the latent response variable formulation. And depending on who you are, you may want to look at the left screen or the right screen. So to make a caricature of people, a statistician might tend to look at the left screen. A psychologist may want to look at the right screen. But, you know, that's perhaps stereotyping the statistician. So we have an ordered Polytomous U. Later on, we're going to talk about unordered Polytomous U. So this is an ordinal variable case. So now we have U equals 0, 1, and 2. And again, they're just labels. So low, medium, high would be a good example, or wrong answer, partially right answer, and totally correct answer. And we're going to have several curves now. We looked at the curve for the U equal 1 category before. We could have plotted also the u equals 0 curve in the binary case. It would have been the complement, so that at any point on x, the two probabilities add up to 1. But since they're so dependent on each other, we only plot u equals 1 curve. So, but in addition, we have a third curve here, u equals 1, the medium or almost correct answer, the probability of which first goes up, but then goes down. So if you think about this in terms of ability testing, x being low down here on slide 49, low x values, you're most likely, the highest probability is for answering the item incorrectly. And then you come up to a higher x value, and then you have a little point here where the middle curve, the bell-shaped curve, is the highest. So for that intermediate ability that you have, you answered the item almost correctly. And then as the ability goes higher, the most likely category to be in is the totally correct answer. You're looking now, if x is observed, this is an ordered polytomous regression, be it loaded or probed. If x was latent, you're now looking at your first IRT curves, item response theory curves, for an ordered polytomous item. And we're going to talk about x latent shortly. This is one way of portraying it, a probability for each of the three categories. It's a little bit more involved reasoning than when you have more than two categories, because you can then change that into two probability statements. You can talk about probability of getting of u equals 1 or 2, getting the item almost right or getting it perfectly right has one curve, and then the probability of getting it perfectly right has another curve. So you accumulate, say, the highest two categories, look at the joint event there, and of course that probability curve is always higher than the getting it perfectly right. And you've seen this situation here before. The parallel curves that Linda talked about on slide 38 had the same shape. And if you look back at that slide, you can say CF slide 38 here. Compare the following to slide 38. And what you find on slide 38 is that these two curves that Linda showed you for smokers and non-smokers, where X was age in the coal mine, differed in terms of an intercept change. But their slopes were the same. The slope for age, beta 2, was the same. You will find the same idea carries through here. And all of this is related to the first day's ANCOVA discussion. So the curves being parallel says that you have one and the same slope, but they are shifted sideways by a intercept or threshold function. Once again, you can turn it into lines by creating the logit, the F or phi inverted. And it's the way we're going to talk about polytomous ordered or logistic regression is a proportional odds model is the term in agresti. Now that may be complicated reasoning, particularly when the statisticians just slap this assumption, top right, slide 49, onto the data or to the model without saying why they do that. More pedagogical, perhaps, is to think about a U-star variable, the specific ability to solve that item. If you're below the lowest threshold, you get it totally wrong. If you're above the highest threshold, you get it totally right, U equals 2. If you're in between of the thresholds, you get it partially right. So you have one ordered U-star variable. So the equation is U star equals gamma times X. And this then explains that you have a single slope on X, a single slope, U star slope. There's a slope for U star. And that's the same thing as the single slope issue here on slide 49, that the curves are parallel. It's one slope. I'm emphasizing that because when we get to the unordered polytomous case, you're going to have several slopes. True, in the ordered polytomous case, we have several intercepts or several thresholds, as we prefer to work with. But you're going to, in the ordered case, you're going to have one slope. In the unordered case, you have several slopes. So the U-star formulation which is relevant for the ordered case, sort of automatically tells you that it will be one slope. Whereas, yeah, I'll stop there. So thresholds are motivated by, we want to have thresholds on an underlying U star. That's why we like to work with thresholds. And they're ordered tau 2 is greater than tau 1 instead of intercepts. So this is sort of, we sort of come from a psychometric point of view here, I guess. And if you want to hear the picture on slide 50 at the bottom, you can parse that and see how the thresholds on an underlying U star for different X values give different U distributions for a 3-category case. So you can work through that visual and see how you feel about it. Here is the mathematics for this. Let's see if I go to 50 over there. Yeah. If you work from slide 50, you will see that these formulas for the probabilities on slide 51 make sense. I'm talking about formulas 74 to 76. Probability U equals 0, probability U equals 1, probability U equals 2. The probability U equals 0 is the probability of being below the lowest threshold. You know, that's the distribution function concept that we talked about. Probability of being below a threshold is, in this case, since delta is normal, it's the normal distribution function. So we're in a probit framework here. Probability U equals 1 is probability of falling below the 2 thresholds. Well, that's that probability is the area under the curve between these 2 lines, which is the same thing as the area of being below the highest threshold minus the area of being below the lowest, right? That gives you the difference. So it's very natural to get to formula 75, which looks forbidding if you just look at that. But if you combine it with a picture, it becomes very clear that it's a difference in phi functions. And then for the highest category, the probability of being above the threshold tau 2 is the probability that U equals 2. Probability of being above tau 2 is the same thing as 1 minus the probability of being below tau 2. So that's worked out in formula 76. All right. And the statisticians instead like to work with the combined events, U equals 1 or 2. And in these formulas on page 52, that's laid out. I'm not going through the details of that. But it shows here, the punchline is, again, 81 and 82. For a probit, the probability of it being the highest category is a linear probit expression. Tau 2 and gamma play in. Probability of being in the 2 highest category is a linear probit, again with the same gamma, same slope. That's the hallmark of ordered polytomous, but with a different threshold. Same slopes of parallel probability curves. Same thing holds for the logit. I'm not going to go through that, but if you go through the pages 53 and 54, you will see that the same concept holds for logit. And compared to slide 50, you can assume then that the U star has a logistic density. That is, in other words, delta has a logistic density. But it's the same idea. Here's an example from an old alcohol investigation in Alameda County. I think that's near San Francisco. Golden, 1982. It's from a book, edited book that I had a chapter in, Muthen, 1993. On the days that you drink, how many drinks do you have per day on the average? And so that's a ordered polytomous variable, 0, 1, 2, 3, where you categorize into non-drink, 1 to 2 drinks per day, 3 to 4 drinks per day, 5 or more drinks per day. So this is like a 6-pack drinking. And then related to age and income as predictor variables. So staying on your right screen, you have the equations for the different outcomes, 0, 1, 2, 3. Just generalizing the formula that we looked at. Same slope gamma, but different thresholds for these different events. You can plot that. Even in the Polytomous case, can you plot sample probits? So here you have, this is from my book chapter, sample probit plotted against age at the top and against income at the bottom. And it's a way to check the model assumptions. So you can plot the sample probit for u equals 1, 2, or 3, u equals 2 or 3, or u equals 3. So these are the accumulated events. And if the model is right, those probit curves for those 3 events should be parallel. You know, we talked about parallel curves for the probits. And that seems to hold well with respect to age. But look at the sample probits for income. They are not parallel at all. They're not parallel, which then says, since they're not parallel, we have a violation of the assumption behind the ordered categorical model. So for some years, when I talked about this example, I suggested somebody should do a dissertation on that. Well, nobody did, but eventually Don Hedeker actually modeled this. So it's a model that's part ordered and part unordered. This suggests that the outcome is unordered with respect to income and ordered with respect to age. So it's a combined ordered, unordered logistic regression. And so Don Hedeker at University of Illinois, Chicago, has written about that. UIC is what it's called. Yeah, that's right. All right. Now let's take a deep breath. We are into a totally different scenario now. We're into the unordered case. And it's equally important. So you can't say, okay, I can do the ordered, but I'm not going to go to the unordered. You just have to buck up here and think unordered. It's going to be so fun to play with. The one example, you unordered when you go to Ann Arbor in November and meet us there. You're coming, right? Haven't decided. Okay. Too cold for California? No, so the unordered case of choice in the Ann Arbor session is going to be a categorical dependent variable that is latent class membership. You try to explain latent class membership by covariates. And that latent class membership is then taken to be unordered. And in a way, the unordered is sort of not postulating any ordering. It's a more neutral approach, right? It's easier to reject the ordered case by plots like the one I showed you. But the unordered sort of takes a neutral stance. And the results will tell you, will suggest that maybe it is ordered. Maybe the categorical variable is ordered. But here we take a neutral stance, and in the Polytomous unordered case, we're going to talk about, and this is a great term, you know, for multinomial logistic regression, perfect for a cocktail party conversation. So you have U equals C, where C is now not only 0, 1, but can go from 1 to up to K categories, say. And the categories are not low, medium, high, but there are bus, train, car, bike, unordered. And you have then this seemingly complex expression, but you're going to become friends with that expression. You're going to really like it. If you break it down, you know, you should sort of, your eyes should ignore the summation sign. Your eyes should ignore the e to the power. You should just focus on the guts, the so-called argument. Although it sounds like a fight, but mathematicians call it argument. Beta 0 plus beta 1x. Well, wow, that's familiar. It's a linear function of x. We have an intercept, beta 0. We have a slope, beta 1. The rest is just noise to our eyes. Although we should make note of the fact that not only do we have intercept with the subscript c, so several intercepts, like several thresholds, but we also have an intercept c for the slope. So we now have several slopes, like the probit plot relative to income. The slopes are not the same. And typically we standardize, so the last category, of the dependent variable u has 0 coefficients. It's unfortunate that in the binary logistic case, the first category is standardized to have 0 coefficients. And in the polytomous case, the last category. And I now regret that we were pulled into that old inconsistency, but we are. So in standard textbooks, you will find this kind of parameterization. Anyway, so what are we talking about here? We can still work with log odds, like in binary logistic regression. And now the log odds in slide 94 is the probability. We're working with the ratio probabilities for a certain category, u equals c, that you're interested in, like having a problem relative to the k category, the reference category, the last category, which is being problem-free. That odds, taking the log of that, is still linear in the beta 0 plus beta 1x. So you can still talk about log odds and therefore talk about odds and odds ratios in this case. But you sort of have to refer to now reference class k here. That looks very strange, but if you look at the special case of only 2 categories, if you take formula 91 and specialize it to only 2 categories, you will get this expression at the top of 59. You get the 1 in the denominator because of the standardization of 0 coefficients. It has to do with the fact that e to the power of 0 is equal to 1. So you scribble here, e to the power of 0 is equal to 1. So these high school math facts. And if you work through this expression, rewrite it a little bit, out comes this expression that we looked at in logistic regression. 1 over 1 plus e to the power of minus the logit. And just another way of writing it is to have e to the power of plus in the numerator, e to the power of plus 1 in the denominator. So those 2 expressions are one and the same for 2 categories, just so you know that, because in some textbooks you'll see the top, others you see the bottom. So now you know that. And that means it's time for me to sit down. Shut up.
I wouldn't say it that way. Okay, so now we're going to have a very short example before Bengt comes back and talks about count data. But just to sort of put this in perspective, all yesterday we talked about linear regressions and continuous outcomes. And now today we've turned to categorical outcomes, both binary and ordered polytomous, and we've looked at the types of regressions that we can have, either probit or logistic. And now for the unordered variable, multinomial logistic. So the scale of the dependent variable defines the type of regression. So whenever you're looking at your output, if you have a complex model, and you want to know what that parameter is, then you just have to remember what the scale of the dependent variable is, and the type of regression coefficient will become obvious to you, hopefully. So anyway, that's something to remember, because sometimes people, they go, I can't understand what the output is, what is each entry? And it's basically just depends on the scale of the dependent variable. The only thing in the Mplus output is going to be a regression coefficient of one type or another. A factor loading is a regression coefficient, and the scale of the dependent variable is going to tell you what the other ones are, or mean, intercept threshold, variance, residual variance, covariance, residual covariance. So really, if you start thinking of it in that framework, and I describe it that way in chapter, wherever the output command is described, I think 11, then you'll be able to, then I think if you try to attack reading your output with that kind of information in your mind, it makes it a lot easier. So anyway, here we have an input for a multinomial logistic regression. Let me do this on the right screen. And this is a simple input where we have just our name statement, name of our data set. And what's new here, though, is nominal equals u. So we're saying that, that u is a nominal and unordered categorical dependent variable. And in the model command, we just regress u on 3 X variables. So U is nominal, and the categories are property of people who have committed property offenses, people who have committed drug offenses, people who have committed, the first one is person offenses, drug offenses, property offenses, and no offenses. So it's 4 unordered categories. And the 3 covariates are age, male, and black. And when we say U on X1 through X3, this is a new shorthand language that we introduced in version 5. You used to need to say U number 1 on the covariates, U number 2, and U number 3. So the last category is the reference category, so we do not refer to category 4. But if you want to refer to a category specifically in Mplus, you use the convention of the number sign followed by the category number. So here we have our results. First column, the parameter estimate, second, standard error, and the third column, the ratio of the estimate to the standard error. And the way with the multinomial logistic regression, we're always referring to the reference class. So if we see that this is significant, the first regression coefficient, it's negative. And the way that we would interpret that is we would say, as age increases, the odds of being in class 1 relative to class 4 decrease because this is negative. And for males compared to females, the odds of being in class 1 in contrast to class 4 increase because this is positive. So this is how you would interpret these multinomial logistic regression coefficients. So now, what else can we do with this information? We have 3 regression coefficients, and how might we turn these results into something more meaningful? How would we compute the probabilities? And this information on the right screen is taken from Chapter 13. Chapter 13 is a chapter where it's sort of like frequently asked questions chapter, when people ask us a question so many times that we finally get to the point that we think we should write it up. So just nag us. That's the best way to get us to write something up. So anyway, we decided to include how to compute the probabilities. So let's take a situation where all the x's are 0. So, and I think 0 means age 16 or something for age 94. And I think 0 is female for gender, and it's white for the ethnicity variable. So if we make all the x's 0, then the logit or the log odds, which is beta 0 plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3, in this case with 3 x's, ends up to just be beta 0, the intercept. So here we have intercepts. And as I said, in the nominal case, we give intercepts, not thresholds. And it's always labeled in the output. If it's a threshold, it's labeled threshold, and intercept, intercept. So the logit or log odds ends up being the values shown on the left screen under intercepts, because all the covariates are 0. So if we exponentiate these values, you get the values under EXP. 0 for the last class becomes 1. And then we take the sum of those because the probability is the exponentiated value divided by the sum. So we get the probabilities of being in the categories for the people defined by these covariates, so females, white females at a certain age. So we can also evaluate it. Whoops. When all of the covariates are 1. Which I'll do over here, so I can remind myself what covariates equals 1 means. Okay, so with all the covariates, it's black males age 17. So we're evaluating the probabilities for black males age 17. And here, the logit or the log odds includes, well, let me just put the results back on that screen. It includes not only the information about the intercepts, but also the information about each of the regression coefficients, the multinomial logistic regression coefficients, times the value 1, because we're evaluating at x equals 1 for each of them. So we get the values shown here at the bottom. So the logits and log odds, if you compute this, become 0.629 for u equals 1, minus 0.1.098 for u equals 2, etc. We do the same thing as we did on the other one, exponentiate, sum, and get the probabilities for black males age 17 of being in the different categories. The property offense is the first category, I think. I can never remember this. Right, the property offense, drug offense, person offense, and no offense. So if we make a decision to, so if we evaluate this at more than more than one value of x, we can then plot the information. And that might be something that we would find useful to present in a paper, for example. I'm going to leave that for you, and I'm going to come and put this one over here. Okay. So here we've evaluated for the black males age 17. We've evaluated at x equal 1 for everything, and then at some other value of x. And we can create these plots where age is on the x-axis and the probability of being in the category. I'm sorry I keep saying class because we do the same thing in latent class analysis. So the probability of being in the categories on the y-axis. The top class here is the person offense class. Then the second one is the property offense class. The third is no offense class. And the last is the drug offense class. And so you can see that as age increases, the probability of being in the person offense class decreases. And the people who had no offense at age 16, as age increases, they come up to have the probability of being in that class similar to the probability of being in the person offense class as it's decreased. So this is just a way that you can take the information if you have one continuous covariate, for example, age, which can be on the x-axis, probability on the y-axis, and then plot the other information within the plot there and give some visual interpretation to the results that you got from the multinomial logistic regression. Okay. And now Bengt is going to talk about another scale type, and that's the censored. So a censored variable. Before he talks about count.
All right, so these are good building blocks for a number of models that don't have categorical outcomes. And we're going to take a look at two examples where we're going to use the categorical variable methodology in such other contexts. One is for a so-called censored normal variable, and the other is for a count variable. In both of those cases, can we use the building blocks of logit and probit regression? Censored normal two-bit regression is what it's often called, can be characterized by data. If you look at slide 66 and look at the left picture and then rotate that in, or either in your head or you rotate your head, the latter being perhaps easier, you will see that you have a distribution for y that has a tail but then a piling up at the lowest point, 0. You have a floor effect. Or as statisticians, they wouldn't stoop to calling it a floor effect. You're censored at 0, is what they say. You're censored at 0. The classic example, James Tobin, who then got the nickname for this model as Tobit by Goldberger, the econometrician, he talked about consumption of durable goods in the last year. Durable goods being something like a refrigerator. And for a large proportion of the individuals in the sample, they did not buy a refrigerator. And then you have the people who did buy, and how much did they spend on the refrigerator. Some people apparently got very fancy ones. There are other durable goods too. So you have a variable that's essentially normally distributed, apart from the fact that you have a very strong floor effect. And I think often we see in real data that situation. And you see then on your left screen that that is a case where we actually work with a underlying latent response variable. In this case, we call it y star, not u star, because it's underlying a continuous variable y, not a categorical variable u. So Tobin came up with a y star notion, and this is, the underlying response variable notion is quite common in econometrics. So if you look at econometric textbooks like we will refer to later on, like Madala's excellent textbook on all kinds of weirdly distributed dependent variables, you will see this latent response variable formulation. Again, the linear regression, we just call the regression coefficients pi 0 and pi 1. So here pi is not 3.14, nor is it the probability. So it's the third use of pi, plus a residual. And here we will find that the variance of the residual actually can be estimated. In the continuous case, the unlimited continuous normal case, the y star is directly observed as y. But now we have a continuous censored case, so we only observe y star as y if y star is in a certain region. Otherwise, it's either observed as a lower censoring point or the upper censoring point. The picture on the right here corresponds to a lower censoring point, CL. It could be censored from above as well, not only from below, like it is there. So you only observe the y star variable in certain regions. So it's a latent variable model. The latent variable becomes observable in this case in the positive region. It's unobserved in the negative region. So you can think of a person or a household having a tendency to make a durable goods purchase that's almost at the threshold, the censoring point, versus a family that's very far away from intending to or thinking about buying a refrigerator. So there is a y star notion that they are different. These people at the piling up point are different. It's a heterogeneous group, but you don't know who's who. But the modeling can tell you by using predictors of this y star variable. So this case then breaks down into two parts. You have on slide 65 probability y greater than 0, that is probability of consuming versus not consuming, is a probit regression. And the model for how much you consume is the last line here. Expectation of y for those who do consume as a function of x is a regression function. But it's not a linear regression function. It's a nonlinear function. You have intercept and slope, and then a ratio of lowercase f and uppercase f, which is the normal density divided by the normal distribution function, is a hazard rate, as it's called in the literature. But for us, what the essential part is that you have a model that has two parts. You have a model for consuming with the predictors of consuming, and a model for how much you consume. So it draws on our probit knowledge. It's typically defined in the probit, not the loaded situation, and it has a weakness or limitation, namely, given the y star formulation, the covariates that are relevant for predicting consumption or not, x in this case, are the same as the covariates for predicting how much you consume. And we will see as we go on here that more interesting models for social and behavioral science applications would be different covariates for predicting whether or not to engage in an activity than predicting how much you engage. That would become more flexible. But that flexibility is not in this classical so-called Tobit model. So censored normal is one possibility that you can work with. Now let's work with another non-normal, non-categorical variable, namely a count variable. And we're going to talk about two models for, or three models plus for count variables. So the idea is that you have in the picture on slide 68 a count variable, we call it u. How many times in the last 30 months did you, let's say, how many times in the last 30 months did you at one sitting consume more than 5 drinks? So binge drinking. Lots of people didn't do that in the last month. Some people did it once, and some people did it 3 times. So you have this typically rapidly descending histogram. It almost like the censored normal with a high piling up, but you know, it's only integers that can be observed, 0, 1, 2, 3, 4, so it's counts rather than continuous values. The Poisson distribution is a distribution for such events, and it has a probability function which uses exclamation points, even, you know, that's very exciting, in other words. And in European languages, that's called R faculty, and I always forget what it's called in English. Thank you, factorial. All right, so anyway, lambda has to do with the rate at which rare events occur, so lambda has to do with the mean. So these curves will look different for different lambda values. But at the bottom of slide 68, and here you wish you were back in the old days with transparencies, you would just scoot this up on the page, right? We have a regression equation for the log rate. Again, statisticians love their logs. So we take the log of that lambda, and that is a linear function in x with an intercept beta 0 and a slope beta 1. That's a Poisson regression. You can predict the probability of being in these different categories for you. The only problem is that, as it says on slide 69, the Poisson model seldom fits the data. Because the Poisson distribution has an assumption built into it that the mean is equal to the variance. And very often data have variance greater than the mean because of this preponderance of zeros, as it's called, because of this very high piling up at 0. A lot of people in the sample don't engage in this activity at all. So then the statisticians have come up with what's called zero inflated Poisson, or zip regression. Great cocktail term, too. Do you do zip regression? Often? Anyway, yeah, we're getting a little punchy here. So, are you going to yank me off the stage? Standard procedure, right? So now we're going to come up, you're going to now see your first latent class model. First latent class model, that is, latent class model is a model with categorical latent variables. We're going to talk about 2 people. Let's take the drinking example. We're going to talk about a class of people who don't drink alcohol. So, and the probability that you're in that class is called pi, probability of being in the 0 class where only u equals 0 is seen. U was the number of times in the last 30 days that you drank at least 5 drinks. But the probability of that is the people who don't drink, who are not drinkers, will have u equals 0, right? They will never have u equals 1, 2, 3, and 4. They wouldn't dream of binge drinking because they don't even drink. And then there are other people who are drinkers, and they are, that's probability of being in the 0 class with u following a Poisson distribution. Sorry, probability of not being in the 0 class. Not being in the 0 class means that you are a drinker, and then the probability for observing the number of times that you binge drink in the last 30 days follows a Poisson distribution. So there, pi is the class that don't drink, and 1 minus pi is the probability of being in the class that does drink. So if you're a drinker, you follow a Poisson distribution, but there are non-drinkers as well. So the key point here is that we have a mixture at 0. So what does that mean? It means that if you observe u equals 0, you don't know why u is equal to 0 offhand. U equals 0 could be a person who's a non-drinker. U equals 0 can be a drinker who just happened to not binge drink in the last 30 days. Two kinds of people can give the same result. That is a mixture, a finite mixture, two latent classes, possibly giving the same value, u equals 0. If you observe u equals 1, you know that the person is a drinker, right? So then their class membership gets vividly expressed or revealed. But at 0, you have a mixture. So you can observe no binge drinking for the non-drinkers, and binge drinking have 0 frequency for the drinkers. The probability that u equals 0 according to the Poisson is this. That scary formula top left on slide 68 turns out to be e to the power minus lambda when u equals 0. And the mixing proportion is 1 minus pi. The 1 minus pi probability that you're a drinker. So that way, you have two reasons for observing u equals 0, and therefore you explain the piling up at u equals 0, which you see in all of your behavioral science data, right? Now, the zip model then implies two regressions. One is the probability of being a drinker or not a drinker, and that's a logistic regression. So you have a logistic regression for being a drinker or not a drinker, and then you have a log rate Poisson regression for those who are drinkers and can assume all the values 0, 1, 2, 3, 4. So again, logistic regression plays in, but it plays in explaining the inflation part, so to speak, the probability of being at 0. So that's a useful technique that's included in Mplus. Zip fits the data much better than regular Poisson. But now in version 5.1, we're also introducing a darling of statisticians, namely the negative binomial. So all these funny names, but they are very, very useful. The negative binomial regression is a regression for count outcomes. So for count outcomes now, we can do regular Poisson, we can do 0 inflated Poisson zip, and we can do negative binomial. So although the word is negative binomial, the outcome is count. So the idea is that we modify the log rate equation. We actually introduce a residual, epsilon sub I, which is the epsilon was not present, that residual was not present in the regular Poisson. It's a latent variable for capturing unobserved heterogeneity, differences across individuals, added with a certain distribution for that epsilon. And by doing that, we avoid the Poisson assumption of mean and variance being the same, namely the log rate, the rate. And the negative binomial separates the mean, which is lambda, from the variance, which has this expression, where a new parameter alpha makes it possible to have the variance different than the mean. So we're going to introduce a new parameter. If that new parameter alpha is 0, negative binomial gives Poisson. So you will, in Mplus, be able to fix that at 0 and you get Poisson. It's called a dispersion parameter. When it's greater than 0, that model gives substantially higher probability for low counts and somewhat higher probability for high counts than Poisson. And those are the two factors that you most often need to be able to fit the data. In fact, that then relieves you of the need for including an inflation part. That the negative binomial may not need an inflation part, although negative binomial also comes with the variations of 0 inflated negative binomial and 0 truncated negative binomial. That is, you can have a model for hospital days stay hospital stay in terms of number of days, and everybody's in hospital stays at least 1 day. So you don't observe 0, so the count variable starts at 1 and goes up. That's called zero truncated. It sounds very technical, but lo and behold, that leads to a so-called hurdle model or two-part model. And some of you are familiar with two-part models, and you will certainly hear more about that in August in growth modeling context, where you handle this strong floor effect type of data, where you have a model for the development of the probability of engaging in binge drinking over time, over grade 7 and up. But you also have a model for how frequently you do the binge drinking. It's a two-part model with counts as outcomes. That would be a so-called hurdle model using a zero truncated, in this case, negative binomial, which we will be able to do in Mplus. Yeah. There's lots more to be said here, but I don't think we should say anything more at this point. But it is an interesting development, and I just want to go to slide 72. I'll go back to slide 71. Slide 72, for those of you who are interested in these kinds of topics, from a more technical point of view, here's a new book that just came out. Hilbe is the software editor of the American Statistician. And he's just released a book, Negative Binomial Regression. It's a whole book on this. And the zero-inflated Poisson came from Lambert, Technometrics, again, you know, borrowing from statistics. Scott Long describes these models very well in his book that we talked about before. Here's Medala's very good classic book, Econometrician. And here is the classic paper by James Tobin. Anyway, if you're interested, those are the statistical underpinnings. In the next coming couple of years, I expect us to see more and more applications of the negative binomial and the two-part hurdle version of the negative binomial for count outcomes. For instance, DSM criteria counts for people developing over time. So in Mplus then, bringing it back home, summarizing here, we have the variable commands of categorical U, defining the dependent variable as categorical, which we do for binary and ordered polytomous. Nominal U is for unordered polytomous, nominal variable. Censored is the censored normal from either below or from above. The picture we showed, the example of household expenditures, was censored from below at 0. And count outcomes, where count, just saying count equals U gives us Poisson. U with parentheses I gives us zero-inflated Poisson. And Linda will now tell you how negative binomial is specified, because I can't remember.
I can't either.
Anyway, in version 5.1, there will be more entries here. You say count equals U, and then in parentheses, I think it is NB for negative binomial. Right. And you can have NBI or NBT for truncated added to that. I don't think we have to talk about the right column at this point, so I'll stop there, I think.
Sounds good. So now we're going to go to path analysis with categorical outcomes. So yesterday we looked at path analysis, but the outcomes were continuous. And remember, path analysis is just a model that contains more than one regression equation. So today we're going to look at a situation where we're interested in high school dropout as the dependent variable. And we have a set of independent variables that are listed here. A female mother's education, dropout thoughts in 7th grade is another one, math score in 7th grade, math score in 10th grade. So what we could do with this data could just be, because high school dropout is a binary variable, we could either do a probit regression or just a logistic regression. So we have, those two choices. Now, we could also instead consider doing a path model. So expanding it to have two dependent variables, math 10, which is a continuous variable, and high school dropout, which is a dichotomous or binary variable. And it would make sense to do this because math 7, the score occurs before the math 10 score in time, and Math 10 occurs before the measurement of high school dropout. So we might want to take those into account in some temporal fashion and pull Math 10 out of the set of covariates and make it be a dependent variable. So, and there's an additional reason for doing that. There's a lot of missing data on Math 10. And if Math 10 is treated as a covariate, then all of the observations with missing data on Math 10 will be deleted from the analysis, because missing data theory doesn't cover covariates, just dependent variables. So if we bring it over here, it's a dependent variable, and missing data theory can apply, and I think it's almost 600 observations that would be lost if we treated it as a covariate. So that's another reason. So there's two reasons for considering a path model in this situation instead of a simple univariate logistic or probit regression. One is missing data on Math 10, and the other is that it takes into account the temporal, the fact that Math 7 occurs before Math 10, and high school dropout is measured after that. So this is the model we're going to look at. As I mentioned, Math 10 is continuous. High school dropout is binary. So the input on the right screen what's new is in the variable command here. We say categorical equals high school dropout. Any dependent variable that's not mentioned is assumed to be continuous. So that way, high school dropout will be continuous. Here we're asking for estimator equals ML. So that means that we're asking for a logistic regression because we don't have the link equals probit here. When you do this type of modeling, you need numerical integration, and we're saying that we want the integration to be Monte Carlo integration. In the model command, we simply do the same thing that we did yesterday in the path model for continuous outcomes. We just specify the two on statements. So high school dropout on female, Math 10, you know, the whole list, and Math 10 on everything except Math 10. So all the covariates here. So just the two on statements are all that we need. And there's really nothing special that, well, one special thing. In the output command, we're asking for the patterns option. So it will show us the patterns of the missing data. We don't give that by default. You have to request that. And actually, let's just look at the output from that. So in the data, we have the missing data patterns, and we have two of them. In one situation, there's no missing data, and in the second situation, there's missing data on Math 10. So that's pattern 2, and if you go down here, you can see that for pattern 2, 574 people had missing data on Math 10. So we would have lost those 574 people if we had left Math 10 as a covariate. Now, tests of model fit, when we get into situations with numerical integration or situations where the sample statistics are not sufficient statistics for model estimation, then we don't get the traditional fit statistics that we're used to seeing. We're not going to get chi-square and chi-square related fit statistics like RMSEA, CFI, TLI, et cetera. Instead, we're going to be getting a log likelihood. I can never get this thing to work. Okay, we're going to be getting a log likelihood. We're also going to be given AIC, BIC, sample size adjusted BIC. In situations where traditional fit statistics aren't available, what most people do are testing of nested models using -2 times the difference in the log likelihood, a value that is distributed chi-square, and which you can then use the chi-square table to look up significance. So further results will be the two regressions. So as I mentioned earlier, so I have high school dropout as the dependent variable on the left screen and Math 10 on the right. And as I mentioned, when you look at the output, you know, what's going to tell you what is in the estimate column is the fact that high school dropout is binary, and we asked for logistic regression. So these are logistic regression coefficients, the parameter estimates. Likewise, on the other screen, Math 10 is continuous, so the parameter estimates are going to be linear regression coefficients. So this is how you decide what they are. And we see here that in the third column, we see that female is a significant positive relationship to high school dropout. So females compared to males are less likely to drop, or more likely, or less likely to drop out of high school. I don't think females are more likely to drop out of high school.
More likely than male. Positive. Yeah, they are.
Well, okay, females are more likely to drop out of high school. As mothers' education increases, the likelihood of dropping out of high school decreases. That's also significant. Math, let's see, math in grade 10, as it increases, the likelihood of dropping out of high school decreases. We can look at dropout thoughts in 7th grade. That's also significant. So as dropout thoughts increase, the probability of dropping out of high school increases. On the right screen, we have linear regression coefficients. Let's see. So here's one: as home resources increase, Math 10 scores increase. There's a positive relationship. Big one here, Math 7 and Math 10, a strong positive relationship, and a negative relationship with dropout thoughts and Math 10. So as dropout thoughts, well, that's not significant, sorry. Arrests. So as arrests increase, Math 10 scores decrease. So, you know, there's nothing special about this. All that we're doing is we're bringing in a different type of regression coefficient. And as I said at the beginning of yesterday, all that Mplus is a simultaneous, when you estimate a model, you're having a lot of different types of regression coefficients and regression equations that are being estimated simultaneously. Now, this morning, Bengt talked about others. Here we have linear and logistic. We could have a path model that has linear, logistic. We could have also censored in there. We could have Poisson, negative binomial. We could have all different multinomial logistic. We could have all different types of regressions in one path model that would be estimated simultaneously. And when you get your results, you interpret it depending on the type of regression coefficient that it is. So. And then we have an intercept for Math 10 and a threshold for high school dropout, because we have thresholds for categorical and intercepts for continuous. Okay, and now we're going to look at one last example, and then we can take questions, which I think is good timing. All right, now this is just another example of a path model. The reference is down at the bottom here. And this is the path model. And in this situation, probit regressions were estimated. And we're showing the U star variables in this picture. So basically, the variables are V, which is father's education, X, which is father's occupation, E, which is education, F, first job, and S, current occupation. But for each of these observed variables, we're showing the underlying latent variable. And the reason that we're doing this is to make the point that for probit regression, something that came up earlier, the mediation variables are treated as the underlying latent variables. So in probit, when you have a mediator and you're regressing E on V, for example, you're really regressing E star on V. But in logistic regression, if you were regressing E on V, you would actually be that's not a mediator, S. So here's a mediator variable. So F.
Regressing S on E.
Okay, S on E. So here we have the mediation. Then you're actually regressing the underlying latent variable for probit and the observed variable for logit. So and it isn't though we couldn't do it both ways for both, but at the current time in Mplus, this is what happens, and you should be aware of it, because let's say that you really want to have the mediation variable be the underlying latent variable, then you should use probit regression in Mplus. And if you want it to be the observed variable, you should be using logistic regression in Mplus. And I believe if you use link equals probit in Mplus, you're also using the observed variable. So probit maximum likelihood is going to behave different than probit weighted least squares. So these are just things that are how we're doing it currently in Mplus. We could open up so everything is done, all possible cells are filled, but we just haven't done that yet. So that's one of the reasons we're looking at this path analysis of occupational destination. The other is to point out something about the data. And so basically, we have two binary variables. And if you'll note, they have a very strong split. We have a 96.4, 3.6 split, 98.3. So, you know, there's very few observations in category 1. And so this is an important reason to use categorical data modeling. And we're going to be talking about later today, when you might want to treat categorical variables as continuous. And you might want to do that for the education variable, because the education variable has a nice distribution. There's no piling up at either end. There's more greater frequencies here in categories 1 and 2 than in 0 and 3. So this is a situation where you could actually consider treating that variable as continuous. And we're going to talk much more about that today and show you, the pros and cons of doing this. Now, should I stop? I guess I should stop now. A little bit more? Okay. So what probit versus logistic regression? So basically, we've already said this is just a summary. So weighted least squares does probit. Maximum likelihood can do either. But, as I just said, this is just a summary, that if weighted least squares uses the underlying latent variable when you have a mediator variable, and maximum likelihood uses the observed variable. But there's a couple of other issues for weighted least squares. We have delta versus theta parameterizations for weighted least squares. The default is delta, and in most cases they're equivalent, and we recommend using the default unless you need to use the theta parameterization, and that happens when you have a categorical latent variable predicting another categorical latent variable which is predicting something else. It doesn't matter what the something else is, but when it's in the middle, then we require the theta parameterization. So if there's a chain of categorical pointing to something else, that categorical in the middle makes us require the theta parameterization. I would not use that unless it's required. In missing data, the difference between logistic and weighted least squares is maximum likelihood allows MAR, whereas weighted least squares allows missingness predicted by covariates. And when you start to do difference testing, if you want to test nested models, with weighted least squares, the WLS-MV estimator, you need to use the diff test option. For WLS-M, you have to use some special directions that are given on the website. For WLS, you can do it in a normal way. Maximum likelihood, ML, you can do it in a regular way. MLR has to have a special way. And MLMV has to use diff test, just like WLS-MV. So I think that's pretty much it. and then references that you might be interested in. So then I think we should take questions and then head out to lunch.
But before questions, this is a lot of complex matters, and it may be useful to just repeat some highlights here. While I remember it, on this page, here is the reference to the path analysis on slide 81. It's in Sociological Methods and Research. It's sort of a curious thing. You can learn from this. In 1987, this gentleman sat in on a course on the predecessor of Mplus, namely ListComp course that I gave in Madison, Wisconsin. And he then went on to become a very famous sociology professor. He's the head of the department now. So good trajectory there. Now, and then just to familiarize yourself, well, I should also mention McKinnon's paper here, a new paper in Clinical Trials, which focuses on mediation when the ultimate dependent variable, the distal outcome, is categorical. He doesn't deal with the mediator being categorical, but he shows then that the indirect effect computations that you have in Mplus is the way to go, the product formula. There are other alternatives. So that's a paper worth reading. It sits on the Mplus website. And just the point, just to strengthen your understanding of pictures like this diagram, at first looks quite complicated. These U star variables are introduced underlying the observed U variables, E, S, F. If you focus on there are three equations here, right? There's the E equation, the S equation, the F equation. The first equation for E, that's just a standard probability regression. We don't need to include E star at all if we don't want to. And typically we simplify our path diagrams so we don't have the star variable in there, the latent response variable. It doesn't make a difference because then it's in standard probability regression, having the U star formulation or not is equivalent. But as Linda said, what makes a difference is that when in the second relation, when you predict from that education variable, then you have to make a distinction. Do you predict from the latent response variable or do you predict from the observed to a later variable? And that makes a difference. If you look at the statistical likelihood, that makes a difference. So you have to ask yourself, is it the event itself that causes something distal, or is it the propensity to engage in the event? So is the fact that you've been held back a grade that event that actually influences a later variable, or is it the propensity to get held back in school? And like Linda said, we haven't filled in all of the possibilities there of maximum likelihood, weighted least squares, U star versus U predictions, but we'll eventually get there.
Okay.
So, and just one more point there, because this is, complicated stuff. This was the high school dropout results. And when you are female, you have a positive sign here. It's very surprising. You always think, girls are good, boys are bad. So, but here, it may have to do with teenage pregnancy matters. And as always, you interpret that not as females being more likely of dropping out, but that holding all the other coefficients constant, the partial effect of being female on high school dropout is increasing the risk. It surprises me too, but I think it is possibly having to do with teenage pregnancy. I don't know. That's to be explored further. Perhaps we don't have the right covariates. So just a couple of points to strengthen your understanding.
And let's take questions. Here's one down here. Probably on the next, a couple pages down.
Slide 80. So the question is, how do you interpret a threshold in a path model like this? And I'll show the picture. Should I?
You're going to show a picture of a threshold?
No,
Oh, that
of the
picture,
model.
okay.
It looks like a towel.
Go ahead.
Yeah, so typically, I think one ignores thresholds until you get to the point where you really want to compute probabilities. Because, it's true that the thresholds are on the probit z-score scale or on the logit scale, but that is tempered by the scale of these background variables. So depending on what the means of those background variables are, the threshold could be high or low. So typically we ignore the thresholds until you get to the point that you really want to compute the probabilities.
Okay, so a little bit like an intercept.
Yeah, it's a little bit like an intercept. It's something that you don't look at at first glance, at least.
But I mean, it's basically the value at which you go from 0 to 1, if you want to think of it that way.
Well, except that in that value,
Right,
you have to take into account all of the
Exactly.
background variables and their coefficients.
But I mean, if you just want an intuitive way of thinking about it.
Right. If
rather-
you don't,
But it's not really of really much interest to report in your results, like Bengt said. But you need it if you want to report your results in probability scale, which you might want to do.
And the dollar sign one would imply that's the
The,
first category to the second category. That's the threshold that happens, which in this case would be going from non-dropout to dropout.
but, yes. But, and it also tells you that that variable is binary. It has 2 categories. If you had number 1 and number 2, it would tell you the variable had 3 categories. So it tells you that too. Question back there? Yes?
As far as on page or slide 78, 79, with that model that you just showed up there, on 78, you include math 10 as a covariate, and then we're using math 10 as a mediator on slide 79. So would you normally do that, or would you not have it as a covariate in your first slide?
So can you put the picture up, Bengt?
yeah.
So high school dropout, math 10. So high school dropout, the reason it's in there is because high school dropout is regressed on has all of these covariates, but it also has math 10.
I think what I was doing is I was seeing this as one analysis, but that's 2 analyses.
Exactly. That's saying you could do a logistic regression or you could do a path model. So it's 2 choices.
Sorry.
No, that's okay.
This model here on slide 74 on the right, the path model, has 2 equations, 2
Right.
dependent variables, that and that. So you get two sets of regression coefficients. It's not 2 analysis, but it's 2 result sections of 1 analysis.
You go.
Okay, lady over there.
The exact same 2 slides. If you're just doing a basic logistic regression, you could in your table give your estimates as well as your odds ratios, as well as confidence intervals and all that kind of stuff. With the path included, can you still, I'm guessing you can't, can you still do odds ratios from those estimates? Or now do you have to, create some sort of scenario to get an odds ratio, like female?
So the question is, in this path model, can you still do odds ratios for the predictors of high school dropout, math 10, and the whole bunch,
So using these logistic regression coefficients.
using the logistic regression coefficient in the column of 78? And the answer is yes. Yeah, you can do that.
So those coefficients directly translate in the same way that a regular.
Yeah, you just take e to the power of these.
Okay.
So they're regular logistic regression coefficients, and you
No.
can treat them regularly.
And as Linda pointed out, it's an interesting idea here that you have this missing data on math 10, and it's not random missingness, certainly. It's very selective missingness in the sense that those who later going to drop out probably have missing data on math 10 because they've been truant and not part of the testing sequence. So it's a really nifty idea, I think. Over there.
The first question, I have 2 questions, and the first is a direct piggyback on that. With respect to your estimates here, aren't these the direct effects? Like, how would would you calculate the indirect effect, say, of any one of those female, moderate,
Right.
and so forth, through math on high school dropout?
Well, it would be the product of the two coefficients, and then you could use model indirect to get the standard error for that. So you would use model indirect for this situation just the same way as you would use it yesterday for several continuous variable regression equations. It's the same thing.
So if we really wanted to know, say, the effect of Math 7 on high school dropout, we would add the direct plus the well, okay.
Can I just repeat that so everybody hears? So the question is, on slide 78, you have the effect of Math 7 onto
High school
dropout, and it's fairly low effect, but that is true. That is the direct effect. It's the parameter of the model are these parameters, right? But Math 7 also has the indirect effect via Math 10, and as Linda points out, model indirect will give you the product of these two. It's a very direct example of the McKinnon et al. Clinical trial paper that I mentioned. So in Mplus, you will get Math 7 will have a strong effect via Math 10. Those who eventually drop out have fairly low Math 7 score, which gives a fairly low Math 10 score, which gives a fairly high school dropout probability.
So the second question I had was with respect to slide 75.
75?
Yeah. Would it be possible to speak only briefly about what's really happening when you say integration equals Monte Carlo 500?
Well, basically, do you want to talk about that? You're saying you need, okay, the question is, what does it mean when you say integration equals Monte Carlo 500? Well, in this situation where you have the categorical outcome, you need numerical integration to estimate the model. Basically, you can choose several different types of integration. And here we're choosing Monte Carlo. The reason you use it is because you don't have a closed form of the distribution, so you have to sort of iterate to get it. So we're just saying that you need numerical integration. It's a special type of an analysis, which you can actually read a brief description of in the user's guide. And you can have various types of settings to the integration option. Monte Carlo is one that can go the fastest sometimes. And you need it when you have missing data. So
just to add to that, because it is a complex matter, natural way of this happening is that you don't include the integration equal. You don't say that the integration thing
equals
there.
Monte Carlo.
And then it will tell you need integration. And then you say algorithm equals integration. And then it will say, well, for this example, you need Monte Carlo integration. So you will be guided. And the reason is that this is actually a partially latent variable. It's missing for some people, but it's not missing for everyone. And that then technically leads to a numerical integration situation, but a very special one that is carried out by Monte Carlo integration. But Mplus will tell you and guide you through that in the science.
It might take 2 steps to tell you, but it'll tell you.
So this is because of you have missing data.
We have missing data on the mediator.
The estimate right otherwise, right?
I'm sorry, so you won't get...
You won't get the estimate right otherwise because of the...
So you're saying the estimates would be incorrect if you didn't use integration?
I think you said earlier that because of you won't have a closed form.
Okay, the question is, why would you need this? It would be impossible to estimate the model without numerical integration.
So just a simple rule of thumb for when you need numerical integration, or very standard case, when you have the combination of categorical observed and continuous latent. This is a continuous latent variable for part of the sample because part of the sample is missing, right? It's like a Y-star variable that you don't observe for some people. So categorical observed, continuous latent, maximum likelihood, that triumvirate leads to numerical integration. Yes, lady in the front.
Yes, and a question back to the indirect effects. Usually we're doing all our analyses in past models are all regression analyses. They're all the same type of analysis. But here you're mixing a categorical with estimates of maximum likelihood with continuous. So how do you prepare these indirect effects, then you use that standardization. Give us some idea how you do that.
So the question is, when you have a combination of continuous and, so the question is sort of, we're used to situations where we have all continuous dependent variables, and we know that the indirect effects are the product of the two regression coefficients. So now that we have a combination of categorical and continuous, what's happening? I think that's what you said. And basically, the same for categorical and continuous, Dave McKinnon has studied this thoroughly, and we base our model indirect on his work. And he has shown that in this case, you can also have the product. So you can have a product of a linear regression coefficient with a logistic regression coefficient, and you will obtain an indirect effect.
Read that paper on the Mplus website.
Yeah. Now, but model indirect only works for continuous categorical or continuous and categorical. Other scale types cannot be involved. We're waiting for Dave McKinnon to figure it out.
Lady in the middle there. Yes.
I'm going to admit I'm basically lazy, and I know that I can figure this out by doing calculations, but for logistic regression, can I get Mplus to print out odds ratios and confidence intervals for me?
So the question is, can she get odds ratios from Mplus in any way, automatically, so she doesn't have to compute them? And the answer is, don't we do that?
Yes, that's given in Mplus, and the confidence intervals for the odds ratios are printed as well.
Excellent. Thank you.
Gentleman in the far back.
If we have a categorical mediator, then what?
So the question is, if we have a categorical mediator, then what? Well, we're not aware of a paper that deals with that. My intuition is that taking the U-star approach that's taken by the pro-bit weighted least squares methodology would give you defensible indirect effect estimates. But I don't have the proof of that, and there's not a paper on that. So if you read this paper, you can create your own little research paper or large research paper and show that my conjecture is either true or false.
So you're suggesting using a probit model to...
Probit model with weighted least squares so that you work with the underlying U stars. So my intuition says that if you work with underlying U stars, if that's relevant, the indirect effect then is with respect to a series of linear regressions for U star. So then you will be in safe haven. Okay, gentleman there? Yes.
I have a question about the difference between a Tobit regression with a censored continuous outcome and how that would differ from transforming a continuous outcome that has a floor effect. Is it just the difference in the questions I can ask whether this happens or not, or the degree to which something happens?
So the question is about Tobit regression or censored normal regression and how that differs from just transforming the variable. So again, do you want to answer?
No.
Sure.
Well, I was going to say that I don't think you can do anything about the floor effect by a transformation. You can't transform it so it spreads out to where it wanted to go, but that's kind of a not very technical way of putting it.
That's what I would say.
Oh, gee. I think you can't, when you have that happening to a variable, that can't be corrected by transforming. Back there in red?
I'm still stuck on the missing data one. I'm trying to think of it in terms of the typical method now, the multiple imputation and the full information likelihood. So this is more like the multiple imputation, or am I way of thinking this data?
Okay, so the question has to do with missing data. Are we doing multiple imputation, or what are we doing here? Missing data is part of, we put that into the longitudinal days in August because exciting missing data facts come out clearly in the longitudinal setting. But this is not multiple imputation, not a multiple imputation approach, but it is the full information maximum likelihood approach to missing data. In large samples, they tend to become the same, one and the same. So there's much more to say about that topic, but that will wait until August. I think we had a lady in red over there. Yes. Yeah, that one. There are a couple of you.
My question is related to slide page 78 and 79. I want to know whether there is a difference between interpreting the coefficients estimate, because it seems like the left one looked like a logistics regression, and whereas the right one is like a normal regression. So
Yes, so the question is the difference between the regression coefficients on the two screens, and when you have a categorical dependent variable, maximum likelihood, these are all logistic regression coefficients. When you have a continuous dependent variable, they're all linear regression coefficients. Any other question? How about here?
I think this is a quick follow-up on the missing data set. Sure. What would you do in a situation where you have a self-estimated variables that are estimated outside of
So the question, I think, is, and correct me if I'm wrong, what happens when you have missing data on your covariates in Mplus and they get deleted? Is there anything you can do about it? Well, there's one thing you can do, and that's you can bring them into the model by mentioning either their means, variances, or covariances. Then they're going to be brought into the model. They're going to still be covariates, but they're going to be distributional assumptions are going to be made about them, whereas no distributional assumptions are made about them when the model is estimated conditioned on them. Do you have anything to add to that?
No, that's what I would say too. So you can assume that you have multivariate normality here, and then the irregular missing data MAR under maximum likelihood will follow. But that's an assumption that you make. The alternative would be to do multiple imputation for these variables, a Bayesian procedure, creating several data sets, and that will have to make some kind of assumption itself, like normality. Right. And then you can actually, then for multiply imputed data sets, call Mplus. So typically you have like 5 versions of your data, 5 imputations. You can send those 5 data sets to Mplus, and Mplus does 5 analysis for you and then summarizes it with respect to point estimates and standard errors, doing the within-between standard error calculation. Those are the two, yes. Yes?
Page 81.
81? Could you repeat the question?
So the question is, can Mplus tell us if the relevant predictor of the distal is E star or E? And at this point, no. But this is something I've been wanting to put into Mplus for some time. What we need is to be able to do maximum likelihood estimation that allows for not only right now we have E predicting S star in the logit setting, we should be able to also have E star predicting S or S star, doesn't matter. So in maximum likelihood, we should have that alternative, and then you can look at the difference in the log likelihood to test. There has been some writing on that. I saw some 15 years ago in the econometrics world. I can't remember where it was, but in any case, that is an empty cell in the Mplus development at this point.
Okay. How about way in the back?
I'm also looking at slide 81. If E and F were continuous observed variables, then an S was categorical. You could just use the regular probit and not worry about numerical integration, right?
Okay, so I couldn't hear if you said S or F here. So could you say that one more time?
E and F are continuous observed variables.
If E and F, as in Frank,
right,
are continuous observed,
and
yeah.
S is categorical, then you can just use, so everything's observed, but
Right.
you have a categorical outcome. You can just use probit, and you don't need numerical integration then.
That's right, yeah.
And then my second question was on slide 71. I just wanted to verify that with ordered polytomous, the reference category is the first category, right?
For ordered polytomous,
So category.
It is, yes, the first category, just like it is for the binary
For
case.
the binary. Okay, great. Thanks.
Any other questions right here?
So I guess I was trying to understand the difference in terms of if you have censored normal data, you know, the difference between COVID and zero inflated Poisson, I mean, which is maybe a better model or
Okay, so
relative advantages.
So is I think the question is the difference between censored and inflated Poisson?
Yeah, COVID and zero.
Well, I mean, to me the difference, and Ben can correct me if he wants to, but, you know, to me the difference
At
is...
my peril, right?
I'm sorry, what?
At my peril.
No. So anyway, censored is a continuous variable that has a piling up. Count is a categorical variable that has a piling up. So they're really for different types of variables. And any other? How about a question here?
I was wondering if you was of difference between zero inflated Poisson and zero truncated. I mean, zero inflated model and zero truncated model.
So the question is, what's the difference between the zero inflated and the zero truncated model for counts? So zero inflated is that you have two reasons for ending up at the zero count point. So you're explaining better the piling up at zero. Zero truncated means that in the sample that you're looking at, you have not a chance to observe u equals 0 because the counts start at 1. You know, the hospital stay, you don't stay 0 days if you're in the hospital. So that's the difference.
Okay, why don't we take two more questions? So here, okay. I'm sorry, what?
What version of Mplus produces the odds ratio and confidence intervals?
I think that's been happening for quite a while. So can you remember?
No.
I mean, confidence intervals, you have to ask for this confidence interval option. But I think we've been doing it. We may not do it when, no? I think
Since
we do
version
it.
3, I would think.
Yeah.
By the way,
If
talking
you're not
about
getting
versions.
it, send it to us and let us know.
Short thing about versions. Mplus is not like Word, where it doesn't matter much if you use a slightly older version or not. You'll have the same bugs in Word. But with Mplus, it's really going forward so rapidly, not only in adding new features, but also speeding up and making things more robust. So always make sure you use the latest version, which is now 5.0.
And actually...